Good morning, ladies and gentlemen. Today we're looking at measurement, and I would like to run through a whole series of formulas that are useful to have on one page so you can see them all at once. I've got a little formula sheet here that you can print out and stick in. It's important to know which part of the formulas apply to what. So let's take a look at perimeter. Very simply, perimeter is the length around the rim of a shape. Think perimeter, rim. And we haven't provided formulas for triangles, rectangles, etc. because you just add up all the edges going around. However, we have for circles. Now, for this shape here, L is this length here. If I just gave you this shape and asked you to find the perimeter of it, you would have to do theta on 360 times 2 pi r plus r plus r. Because the perimeter of the shape includes these edges here and here, which are the r and the r. So make a note to yourself when you stick this in that you want plus r and plus r, because r is these bits as well. If you just want the curve, or the length around the arc, then use this bit here. And we'll use this later on a lot with spherical geometry, because you can imagine that length could easily be the length around the world, or a portion of the world. Alright, looking at area questions. Area, kite, x and y. Height, base of a triangle. We'll do more on triangles below, but it's important to remember that the height of a triangle is not always an edge of the triangle. So many people would look at this bit here and say that's the height. It's not, it's the perpendicular height. And note that the base isn't always the one lying on the ground. It's possible they might give you this as the base and tell you this height there. Alright. Parallelogram is just base times height. Trapezium. Note, when you see a trapezium, so often people are tempted to cut it up into triangles and rectangles. Honestly, just use the trapezium formula. It's much easier. Circle. And sector is a portion of a circle. Note the theta on 360 is essentially what fraction of a circle we have. If that theta is 180, it means we have half a circle. Similarly above, if that was 180, it means we have a semicircle. Alright, surface area. Surface area of a hollow cylinder is this. Surface area of a hollow can, as in with one end, is the same as above, just with this, with both ends here. So quite simply, pi r squared is the area of a circle, so with two ends, we have 2 pi r squared. Hollow cone, pi rs, will give you this, it's the curved party hat surface, so this bit. I can't colour in. However, if you have a solid cone, as in including the base, then you guess that we add a pi r squared to it. Sphere is 4 pi r squared. Note that if we have half a sphere, so a semisphere, alright, it is 4 pi r squared on 2, that's a semisphere, plus pi r squared, because that pi r squared gives us the base that we've been cut through. So if you take a solid sphere, cut it in half, that's what you get. Alright, volume. People tend to struggle with volume, and it's best to keep it easy. Try and think, does it have a uniform cross-section? Uniform cross-section is where it is the same the whole way through. So you can almost think about it, I think about it as slicing bread. If when you make a slice, the slice will be the same the whole way through, then it has what's called a uniform cross-section. Sometimes we call it area of end, or area of base, but either way it's uniform cross-section. It doesn't have to be standing on the base for it to be the base. Right. Now, the area formula for a volume, the formula for volume is very simple if it's a cross-section. So if it has a cross-section, looking like this, then the uniform solid's volume will be area of end times length, or area of base times length, or area of cross-section times length. Other case you're likely to come across is pyramids, or cones, any tapering solid. So any tapering solid that disappears to a point, it might have a triangular base, a square base like this one, it might have a circular base, it might have a hexagonal base. Either way, you have to find the area of the base, times it by the height, and then divide it by 3, or do a third area of base times height. Finally, sphere, 4 and 3 pi r cubed. Note the cubed there. We say pi r squared so often, people tend to put pi r squared there. Alright, moving on. Now, find the volume of this shape. Firstly, let's recognize that the base is not this rectangle here. The base is, or the area of the cross-section, is this portion here, because that's the same that will be the whole way through. So I would write very simply that volume is equal to area of base, or area of cross-section, area of base, times the length, or height. In our case, area of base is a trapezium. So trapezium formula is A plus B on 2 times H times the height of the shape. Now it's confusing because we're using 2 H's there, which really isn't ideal. But remember, this is the trapezium, and that is the height of the shape. So volume is equal to 10 plus 15 over 2 multiplied by 6, and that is then multiplied by 25. 10 plus 15 is 25, times 3 is 75, volume equals 75 times 25. Volume is equal to, I'm not doing that in my head, 1,875 centimeters cubed. It's important that cubed is there because we just worked out the volume. And note, that cubed is not applying to the number, it's applying to the units. So often people say 6 centimeters cubed, they seem to think that is 6 cubed centimeters cubed. Don't know why, but let me just assure you that the cubed is only applying to the units, not the 6. Alright, one more example. Find the surface area and volume of this shape. Now, surface area and volume is a little tricky. It's easy, rather, but needs to be done methodically, otherwise it's very easy to make a mistake, which is what makes it tricky. If I was going for surface area, and we'll do surface area first, best thing is to draw a net. Now a net will start generally with you drawing the floor. The floor of the shape is this 35 by 10 centimeter rectangle that goes along here. Then imagine there's a little man inside pushing the walls down. Say he pushes this wall down here. Add in the measurements as you go. You know that this is 20. You know that this is 23 here, and this is 20 there. And he's pushed down the wall on the other side. The scale doesn't have to be perfect. The important thing is you're getting every single side. 20, this is 20 as well. Then we want a wall this way. That's this wall here. Shoving that wall down will be 20 as well. The other wall, 20. And then 2 walls on top. So I have to zoom out a bit to get these in. The walls on top will be this bit here. That looks like this, with a length there of 29, because that's this length here. And another one here, scale doesn't actually matter, 29. Alright, now we want to find the area of all these different sections and then add them up. So, keeping it nice and visual, area in here, let's do the rectangles nice and easily, is 20 times 35, which is 700. And we know that this is the same here. This here is 10 times 35, 350. This is 10 times 20, 200, which means it's the same over there. This is 10 times 29, so 290. 290. This here is 20 times 23 times a half, because triangle is a half base times height. And you should be checking the formulas above if you need. Half base times height will be 230. Same again here, 230. And then the total surface area is the sum of all of these sides. So I'll pause while I add this up, but you should be able to go through it nice and systematically. And our answer is 3,190 centimeters cubed. Right. That's surface area, not cubed, because it's surface area. If we're working with area, squared. Volume now. Volume is almost easier in this case because we have already found the area of the cross-section. The cross-section is the bit that's the same the whole way through. It's this portion here. And that's volume equals area of base, or area of cross-section, times the height, AOC, AOB. Area of the cross-section is 930, because it's the sum of these two. And then it's multiplied by the height, which is 10. So our volume is 9,300 centimeters cubed. And note, it is possible to have a volume that's smaller than the surface area. If this thing here was only 1 in height, then its volume would be smaller than the surface area. So don't freak out if you see that. Alright, I will end the video here. We will do plenty more examples of these in class, and I'll try and make them a little more interesting as we go. Thank you very much.